Welcome back to Differential Calculus. In this video, I want to talk a little bit more carefully about trigonometric functions. I've mentioned previously a couple of ideas related to trigonometric functions. Let me just gather them all here for the sake of convenience. There are many trigonometric functions. The four that we are going to be concerned about in this course are sine, cosine, tangent, and secant. One of the properties of all trigonometric functions is that they are periodic. For example, the sine of x, and we are going to always assume that our angles are in radians. I know a lot of places you worry about degree measure. I apologize to anyone who is taking calculus and physics simultaneously, where you do all radians all the time here and all degrees all the time there. But we are going to work with radians exclusively. Trying to do calculus with angles in degrees really makes you want to tear your hair out. It makes everything more complicated, and calculus is complicated enough without that. But in radians, 2 pi is the distance around a complete loop of a circle. So sine of x plus 2 pi is the same thing as sine of x, which means that sine has period 2 pi. One of the interesting things about periodic functions, depending on how you define the vocabulary, because it is true that sine of x plus 2 pi is equal to sine of x, it is equally true that sine of x plus 4 pi is equal to sine x, right? 4 pi is just 2 pi twice. So subtract 2 pi, sine of x plus 4 pi is the same thing as sine of x plus 2 pi. Subtract 2 pi again, sine of x plus 2 pi is the same thing as sine of x. It's twice through the period. But depending on how you care about the vocabulary, you could claim that sine x also has period 4 pi. There are times when that sort of terminology can be useful, especially when you're dealing with several trig functions combined. Because sine, cosine, and secant all have period 2 pi, and any multiple of 2 pi is also a period of the function. Tangent has period pi. Tangent goes through its period twice as fast as the other trig functions. And so when you are looking at something that combines tangent and secant, thinking about tangent as having period 2 pi, even though its period is actually pi, can be of some value. When we are working with trigonometry in this course, we are almost always going to end up at one of the special angles. The special angles are 0, pi over 6, pi over 4, pi over 3, and pi over 2. Unfortunately, no, pi over 5 is not one of the special angles. I have seen people make an argument that pi over 12 and 5 pi over 12 are also special angles. We tend to leave them out because they're a little bit more complicated. In degrees, this is 0, 30, 45, 60, and 90. And the reason that we care about these special angles is that they are the places where we can give an exact value of the trig functions. Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is the square root of 2 over 2. Sine of pi over 3 is the square root of 3 over 2. And sine of pi over 2 is 1. One of the big advantages of the fact that we're always going to work with these special angles in this course is that it allows us to do our work without needing a calculator. But that means that you need to know these special angles or have them written down on a reference sheet when you're allowed to use a reference sheet. There is a trick that makes it fairly easy to remember how to construct this table, whether or not you can remember which one is which an immediate callback. I will admit that I kind of have to go through this whole table every time, so it's not weird if you can't either. I'm going to write the nicer looking of these values in the most convoluted way possible. And I'd like you to take a minute and verify for yourself that the square root of 0 divided by 2 is 0, the square root of 1 divided by 2 is 1/2, and the square root of 4 divided by 2 is 1. Once you have that, once you are convinced of what's happening here, now look at this pattern. It's just counting. 0, 1, 2, 3, 4. Take the square root of that number, then divide by 2. So if you can remember the names of the special angles, 0, pi over 6, pi over 4, pi over 3, and pi over 2, and you can remember how to count, then you can fill in the value of sine at each of those special angles without much further thought. Cosine is just the same thing backwards. Excuse me. Instead of reading from left to right, read from right to left, and you have the values of cosine of x. I'm going to go here straight to secant. The secant of x is the reciprocal of cosine. So you get 1. You get, well, I guess it would be 2 over the square root of 3, but we usually rationalize that and call it 2 root 3 over 3. I guess it would be 2 over the square root of 2. But that actually simplifies just down to becoming square root of 2. Then it's 2, and then it's, well, 1 over 0, which is undefined. All right, so it's getting messy, but it's still there. As soon as you know how to figure out and write out this list of sine, you can write out the rest of the table without too much thought. Last thing here is the tangent function. Tangent is sine divided by cosine. So take the entry for sine, divide by the entry for cosine. 0 over 1 is 0. 1/2 over the square root of 3 over 2 is 1 over the square root of 3, which we generally rationalize and write as root 3 over 3. I'm running out of room, so I'm not going to write out the rest of these calculations. Root 2 over 2 divided by root 2 over 2, that's easy. Something divided by itself is 1. Root 3 over 2 divided by 1/2, that's just root 3. And 1 divided by 0, again, is undefined. That gave us the vertical asymptotes in the graphs. Again, I'm not going to say that you need to have these memorized. You can use a calculator to figure these out, and I'm not going to ban you from using a calculator in this course. All right, just to show you what I mean there really quickly, let's take sine of pi over 4. If I don't quite remember that sine of pi over 4 is root 2 over 2, but I remember that it involves a square root somehow, I can put sine of pi over 4 into my calculator, and then I can square it and get that, oh, sine of pi over 4 squared is 1/2. So sine of pi over 4 must be the square root of 1/2. And if you rationalize that, you get root 2 over 2. So you can learn these exact values. You can have them available as a quick reference. You can learn how your calculator produces them. This calculator is one of the harder ones to use. There's a lot of calculators that you put in sine of pi over 4, and it just gives you root 2 over 2 without you having to do any work at all. These tools are all available. The important thing here is recognizing that exact values are a thing in the first place and recognizing when you can use them to your advantage. So again, in this course, we're going to work with exact values pretty well exclusively. We do that because it allows us to have nicer results. It allows us to do our work without relying on a calculator, and that just allows us to work that little bit faster. The other thing that I want to mention in this video are some of the trigonometric identities. There are a lot of trigonometric identities. For right now, the ones that I want you to be familiar with are the ratio and reciprocal identities, the ones that tell us how the trig functions relate to each other, the ones that I just was talking about. Tangent of x is sine of x over cosine of x, and secant of x is 1 over cosine of x. Those are the ratio and reciprocal identities. The other ones you should know are the Pythagorean identities. The classic one, sine squared of x plus cosine squared of x is equal to 1. But then if you divide both sides of this equation by cosine squared and you use the ratio and reciprocal identities, you can rewrite this to get that tangent squared x plus 1 is equal to secant squared of x. That's a second Pythagorean identity. You have almost certainly seen other trigonometric identities in previous courses, right? Typical trigonometry or pre-calculus course goes through all these other things. The angle addition formulas, the power of reducing formulas, the sum to product of sum formulas, double angle and half angle formulas. Those are certainly useful in a lot of applications. And for those of you who are going to be continuing in calculus, the second semester of this course uses a lot of those. But for our purposes for this course, this shorter list is good enough. We've talked about transformations of graphs already. When it comes to transformations of trigonometric graphs, there's a little bit of vocabulary that I want you to be familiar with. I'm going to look specifically at the sine, but the same general ideas will work for other trigonometric functions as well. So A times the sine of B times X minus, and used to be H. I'm going to write the Greek letter phi here instead. It serves the same purpose. But by putting phi here, it emphasizes the fact that this is an angle. We call that the phase angle. And there's a lot of applications of trigonometry where thinking about whether sine waves are in phase or out of phase is important. We're not going to look at that in particular, but mentioning the vocabulary is useful. I want to mention here that A controls the amplitude of the function. And the other thing that I want to mention here is that the period of the new graph is related to B, but not exactly the same. Remember that if you increase the value of B, it brings the function tighter together, which means it has a shorter period. Larger B, smaller period. If you decrease the value of B, it spreads the graph out, giving you a longer period. Smaller B, larger period. And so the relationship here is going to be take the period of the original function and divide by B to get the period of the transformed function. And for sine, the period is 2 pi. So if I'm looking at y equals 2 times the sine of 4x, that means that the amplitude is going to be 2, and the period is going to be 2 pi over 4, which is pi over 2. Using that information, I can sketch this graph out. I know what a sine wave looks like. And when I'm doing transformations like this, very often I get a little bit cheeky and I graph out. Here's what a sine wave looks like. I do try to always remember to include more than just one full period to remind myself that it is going to continue onward. It's not quite so important for sine, but for cosine, I see a lot of students make some weird mistakes, forgetting that the graph is supposed to turn back around at the end of the period. But I know that the amplitude is 2. So this got up to 2, and this got down to negative 2. I know that the period is pi over 2. So this point right here must be pi over 2. Halfway between is going to be pi over 4. That's going to be where it crosses the x-axis in the middle. And then the peaks, the maximum and the minimum, are going to be halfway between those. In this case, that must be pi over 8 and 3 pi over 8. We can think about looking at the picture, looking at what the amplitude is, looking at what the period is, and use that to figure out what our graph is supposed to look like. We can also think about that in the other direction. So if I sketch out a graph that looks like this, I have positive 5 and negative 5 on the y-axis. I have 10, 20, 30, and 40 on the x-axis. And I have a sine wave that kind of, not all the way down there, only to there, a sine wave that kind of plays connect the dots. From this graph, I would like you to tell me what is the amplitude and the period of this sine wave. Then A times the sine of bx minus phi. What are the values of A, B, and phi that give us this particular graph? All right, so take a couple of minutes to think about that, see where you can get with it, and I'll see you in the next video.